Okay, Calc students, this is section 2.3. And I wanted to start off with the main slide here on the PowerPoint, which just want to remind everybody that when it's time for a new section in this class, that there will be on Google Classroom, there will be the slides presentation, a link to WebAssign, and also a link to this video lecture. Okay, so just so you know. So I didn't want to put this in full present mode, but these limit laws, okay, are important. So essentially the first one just says if you have the limit of two functions added together, you can separate it into the limit of the first plus the limit of the second. Same thing with difference, same thing with product. Product of a scalar, if you just have like c times a function, you can pull the c out in front. If you're multiplying two functions together, it's the limit of the first times the limit of the second. And then same thing with the quotient if you're dividing by 1. Okay, the thing here though is that you have to remember that the limit of g of x cannot equal 0. Okay, so I just wanted to make you guys aware. It's almost like the limit can kind of be distributed through, if you will. So these limit laws are important. So now, instead of going through every slide on the PowerPoint, after I looked through them, I really thought after we talked about the limit laws for a minute, and then there's also a squeeze theorem that I'll come back to in a minute. I really thought going over the homework problems in WebAssign would probably be our best bet. So here we go to our homework problems. Okay, so given that the limit of f of x equals 4 as x approaches 1, and the limit of g of x is -2 as x approaches 1, and the limit of h of x is 0 as x approaches 1, we have to find all of these values, okay? And we're using those limit laws. So, for instance, this first one, we're going to use a couple of the limit laws. So we're going to use law 1 and law 3 here, if you kind of remember. So this is going to be broken out, the limit of f of x as x approaches 1 plus 4 times the limit of g of x as x approaches 1. Okay, so that's using the limit laws 1 and 3. So if f of x as x approaches 1 is 4, then this becomes the number 4 plus 4 times the limit of g of x is -2. Okay, so this is 4 plus a -8 or -4. So that would be the answer here is a -4. Okay, do you all see what I'm doing there? Okay, using the limit laws. So this is the same thing as part B here. The limit of g of x as x approaches 1 cubed is going to be g of x is -2. So this is -2 cubed or -8. So you're literally just substituting in the limit, okay, and then taking the operation. So this one, you're actually taking like the square root, I'm not going to finish it, but the square root of the limit of f of x as x approaches 1. Okay, that's limit law, actually limit law 11. We didn't get through all, we went through the main ones. So I think you kind of get the idea here on these, okay? You're just applying the limit laws. All right, now let's keep going. On the smart ink, I have to erase each page before I can go farther. So now evaluate the limit using the appropriate limit laws. If an answer does not exist, enter D and E. Okay, so let's take a look here at number 2. We need to apply the limit laws so that we can evaluate this. Okay, so let's start breaking this up. So this is the limit as t approaches 2 of t to the fourth minus 9 over, we're going to apply the limit to the top and the bottom. The limit as t approaches 2 of 2t squared minus 3t plus 5. Okay, so then we're going to kind of break everything out again using the limit laws. So this is the limit as t approaches 2 of t to the fourth minus the limit as t approaches 2 of 9 over 2 times the limit as t approaches 2 of t squared minus 3 times the limit as t approaches 2 of t plus the limit as t approaches 2 of 5. Whew. Okay, now in each one of these, this, okay, turns into a 16, right? 2 to the fourth. This one remains a 9. That's a constant function, 9. It's just a constant horizontal line at 9. Doesn't matter what t approaches. It's always going to be 9. This one is going to be, you put the 2 in for the t, so 2 squared is 4. So we're going to have 2 times 4 down here, minus 3 times 2, again, if we plug in the 2 for the t, and this again stays 5. Okay? So if we do all of this math, this is going to give us 16 minus 9 on top over 8 minus 6. Well, we're going to have 7 on top. 8 minus 6 is 2 plus 5 is also 7. This just equals 1. Okay, so the limit of all of that is just 1. Okay, essentially, I wanted to show you what they're doing here with all the limit laws, but let's cut to the chase here for the next one. What we're essentially doing is plugging a 2 in. Okay, so like if you look down here at number 3, we are plugging a 2 in place of both of the x's. So this is essentially the square root of 3 times 2 squared plus 4 over 3 times 2 minus 2. So 3 times 4 is, this is 12 plus 4 over 6 minus 2 square root. Okay, you guys with me? Okay, so this is square root of 16 over 4. Okay, which is the square root of 4, which is 2. Okay, so that's really all we're doing. I just wanted to show you on number 2 there, as we went through all the steps to break it out, why it is what it is. Okay, so really, as long as we don't get anything weird by substituting in what our variable approaches, like any zeros on the bottom or anything, we're okay to just plug it in and see what it gives us. Okay, hope that is helpful. Now, moving on. This one, what is wrong with the following equation? Well, if we kind of look down through the options, and I'm not going to go over this in detail, I'm not going to give it to you, but the first thing that jumps out at me in part A is that what value of x can I not have on the left-hand side? Okay, over here on the left-hand side of this, x cannot be 4, right? Because that's going to make my denominator go to 0. So that's one thing, okay? So I have to be kind of careful there. The left-hand side is not defined for x equals 4, but the right-hand side is. That would definitely be your answer, okay? And then I'll let you guys finish that one, but that's kind of where they're going with those, all right? The next set. So evaluate the limit if it exists. If an answer does not exist, enter D&E. Okay. This is where, what's going to happen on number 5 if I just plug this 2 into here? I'm going to get a big fat 0 on the bottom, right? So that doesn't work. I can't just plug it in like I did on, what question was that, 2 or 3? Okay, I can't just plug it in like I did on those. So what do? First thing you should always try to do is get rid of the denominator if you can. So in this case, what jumps out at me here is this, I'm going to rewrite this as limit as x approaches 2. I can factor the top. This factors to what? -2, -1. And this is x minus 2 on the bottom. Now what do you notice? Now I can cancel out the x minus 2's. So now I'm left with the limit as x approaches 2 of x minus 1. Now, can I plug 2 into that? Of course I can. Okay, so now I can take this 2 and plug it in here. This gives me 2 minus 1, or just 1. Okay, so if you can simplify the rational expression, or the polynomial fraction, if you can simplify it, you should. Okay, that'll help you find the limit. Now, what about this one, number 6? Evaluate the limit if it exists. Okay, once again, as I look at this, I know that if I put in a 1 here in place of my x, this goes to 0 in the denominator, and I can't have that. So the next thing that I think about is exactly what I did in the problem above it. Okay, let's see if it factors. Okay, so I've got limit as x approaches 1 of, let me factor the top. Factors of a positive 15 that add to -8 would be -5 and -3. Okay, over x minus 1. Well, here's the problem. Nothing cancels. Okay, if nothing cancels, then I got a problem. So this is actually DNE, does not exist. Okay, if it's going to give you an ugly denominator like 0, doesn't exist. Okay. Let me erase here before we move on. Okay, moving right along. Evaluate the limit if it exists. If an answer does not exist, enter D and E. Okay, what can I do here? Well, right now, again, if I put a 0 in for H, that makes my denominator go to 0. So I'm looking at it wondering, how can I simplify that? Well, the first thing I can do is actually multiply out or expand that -3 plus H binomial that's squared. Okay, if I expand that, if I multiply it out, this is going, I'm just going to rewrite it. Again, the limit as H approaches 0, this is going to give me, if I multiply out -3 plus H times -3 plus H, I am going to get 9 minus 6H plus H squared, and then I've got the -9 up here, all over H. Are we okay with that? Again, all I did was expand out the binomial -3 plus H that was squared. Okay, now you'll notice that my 9's here will cancel, and then what I have left is the limit as H approaches 0 of H squared minus 6H all over H, which actually, let me rewrite that. Let's pull out an H. So I can factor an H out of the top. That's going to leave me with this. Okay, so then what do you notice? Then my H's can cancel. This one that I factored out anyway. So now I've got the limit as H approaches 0 of H minus 6. Well, now can I put 0 in for here? Absolutely. So this is going to give me 0 minus 6, which is just -6. Okay, so that would be my answer on this one. Okay, now the next one, I was going to say you all can do that. Let me give you a tip on the next one. I'm not going to work it all out for you, but again, I can't cancel any h's, and my h on the bottom can't go to 0. So let me give you a tip. Here's how you start this one. Think about this numerator being a binomial. We've got the square root of 25 plus h, and then the minus 5. Those are my two terms. So multiply the top and the bottom by its conjugate. So 25 plus h plus 5 on top and bottom. Square root of 25 plus h plus 5. Multiply that on top and bottom. Okay, what happens there? Then we get up here, we get, I should keep going with my limit here. Limit as h approaches 0 of the square root of 25 plus h squared minus 5 squared all over h times square root of 25 plus h plus 5. Okay, so I'll take it one more step and then I'm going to leave you guys to finish it. So the limit as h approaches 0 of, on the top, this leaves me with the square and the square root cancel, right? My square root and my square cancel. That leaves me with 25 plus h minus 25, okay, all over this times that. Don't distribute that h through, leave it outside on the bottom. Because what's going to happen now, I'll just kind of talk you through it. These two are going to cancel, right? Then what else is going to happen? This is going to cancel with that. That leaves you with a 1 on top and just this on bottom. A 1 over that. So then what's going to happen when you put 0 in for h? Okay, what's your limit going to go to? I'll leave you guys to finish it. Okay, so I got it started there. So if you have some ugly binomial in the numerator, you can also multiply the conjugate by top and bottom. Again, the goal is to get rid of the radical on top so we can have something to cancel the h with that's on the bottom. That's the goal. Okay, so anytime you have like a single variable or something on the bottom that's prohibiting you from solving the limit, see what you can do to cancel it out. So that's why we multiplied the top and the bottom by the tops, by the numerator's conjugate, so that we could cancel out the square root. We didn't care that we were adding a square root to the bottom because we knew it would all work itself out in the end. The goal was, again, to get something with an h on top so that it would cancel with the h on bottom. Okay. All right, hope that was helpful. Let me erase and then we'll keep rolling through the assignment. Okay, the next one, my tip to you on this one is, again, to multiply this part out. Okay. Multiply that out. I don't know if y'all remember the binomial theorem or if you just want to literally take x plus h times x plus h, get the answer, and then take it times another x plus h. Or if you remember the third row of Pascal's triangle in the binomial theorem from Algebra 2, you can use that as well. But expand that, okay? Expand that out, and then I think you'll see all the stuff that will cancel, and then you can evaluate it, okay? Now we are getting to the squeeze theorem, which is the other thing I kind of wanted to point out. Let's see if my link works here. Yay, it does. Okay, here's the squeeze theorem in a nutshell. If we have some g of x, okay, if this is between these two, so f is less than or equal to g is less than or equal to h, when x is near a, except for possibly at a, and if the limit of x and the limit of h equal the same thing, then the limit of g has to be the same thing. So they're saying if you've got some function on top, some function on bottom, the limits are the same, then the function that's in the middle also has to have the same limit at the same point. Okay, which that kind of makes sense. That's why they call it the squeeze theorem. G of x is squeezed between f and h. And so if f and h have the same limit at a particular point, if g is between those two, then it's got to have the same limit. Again, I think that's fairly intuitive. So I think you can kind of see that. So back to our homework then. Use the squeeze theorem to show that the limit as x approaches 0 of that whole big hunk of mess is all now. This one I'm just going to help you by showing you a graph. Okay, so let me go back to here, and I actually Desmosed. There we go. So here's, I even labeled them f of x, g of x, h of x. So f of x is the red. Okay, this is the red line. G of x is the blue. Okay, it's the cosine function, hence I kind of zoomed in so you all could see all the squigglies. Okay, remember your cosine function, up and down and up and down. Okay, and the h of x, because it's the positive x squared, is the green. Okay, and of course I'm writing it in purple, but you get the idea. Okay, so what this is saying is that if f of x and h of x have the same limit at a particular point, like, oh, say 0, if the limit is 0, then the limit of the cosine function that's between those two is also going to be 0. Okay, that's the moral of the story. Okay, does that make sense? So as we look through here, let's go back to the assignment. So these have little drop-down menus. Okay, so cosine of 23 pi x, good gracious, without the x squared on it, is between, I will just tell you, if you graph, and I didn't take the time, but if you graph cosine of 23 pi x, well, first of all, let's just talk about cosine. Any cosine function oscillates between what two numbers? Okay, your traditional cosine function, if you remember cosine of x, if we've got our graph, it starts up here and does this business, right? So like this is pi, this is 2 pi, if you remember. What's this number and this number? What does it oscillate between? It oscillates between 1 and -1, if you remember correctly. Okay, every cosine function, regardless, all this 23 does, if you all remember, is change your period. Okay, so it just changes the width, essentially, of the curve. So all of your cosine functions are going to oscillate between a -1 and a +1. Okay, I just kind of got you started there. And then f of x, well, okay, sorry. Then the function, it's double arrow here. So first we know that the cosine of 23 pi x oscillates between -1 and 1. The function that we're talking about that's got the x squared on the front, you could see by my Desmos graph, oscillates between f of x, whoa, why did that just drop? I have no idea, and h of x. Okay, it oscillates, it's between those two functions. F of x on the low side, h of x on the high side. So I'll let you all fill in the last two blanks. Okay, should be pretty straightforward. But that is the squeeze theorem. If we have a function that literally falls between two functions, if the two functions have the same limit at a point, then the one in the middle has to have the same limit at the same point. Okay. This one, number 11, I think I'll let you have at. It's not too bad. 12. So we've got find the following limits. That gives us, we've got a piecewise function going on here, right? Y'all remember piecewise functions where we restrict the domain? Okay, so for all x's less than 1, this top one is our function that we're graphing. For all x greater than or equal to 1, this is the function that we're graphing. Okay, so it's totally restricted on our domain. Now, let's think for a minute what x squared plus 2 and what x minus 3 squared equals. X squared plus 2, let me just remind you, is a shift up 2. So again, instead of being at 0, 0, it's at positive 2 and it points up. Okay. Now, in the same vein here, the next one, the x minus 3 squared, is a shift what? The minus 3 is actually backwards. It's a shift right 3. Okay, so again, instead of it being centered at 0, 0, it's actually going to be centered at 3, 0 and go up. That's what they're going to look like. But what we have to be careful of is the restricted domains. Okay, so this one is for all x greater than or equal to 1, which means we essentially cut this part off and it's just this side. Okay. This one, the top one, the x squared plus 2 is for all less than 1. So we essentially cut here at 1 and this is all gone and we're just looking at this side. And it doesn't include 1, so we'd have an open circle there. Okay, I pretty much gave that away. So you've got, I would personally do part C first, where it says sketch the graph. I would do part C, and then from the graph, I think you can easily tell then your limit from each direction, what it's going to be. And then again, remember, when you're talking about limits from the left or limits from the right, they have to equal the same number if the overall limit exists. Okay, so that's going back to kind of what we did before. Is that it? That's it. Okay, so that is this 2.3 section. I hope this video helped, and I will be making more lecture videos for each of the sections since we're going virtual. Be checking your Google Classroom, okay? And everything will be posted there for the videos and the PowerPoint links. All right? And if you have any questions, email me.